Hey everyone, how's it going? I'm coming to you from the suburbs of Baldwin, Illinois. When I was little, the hustle and bustle and the traffic and the noise of Baldwin, Illinois was just too much, so we moved out here to the suburbs. Anyway, um, I just wanted to talk to you a little bit about another inferential stat that we use and that you're going to run into quite a bit. And so let's do that. Let's talk about linear regression. And so when would we use this? Let's set up a theoretical example. Let's pretend that we're studying the effect of carbon dioxide as a fish anesthetic. Well, that's not far-fetched. This is something that we've done a lot of work on, and it works very well for, a lot of times we need to knock out a fish. Sometimes we just want to calm them down so we can measure them. Sometimes we want to do surgery. CO2 works really well. But we're trying to figure out like how much CO2 and how long the fish will be knocked out. So we got a small tank, and we'll put a single bluegill in it, small type of panfish, and then we just add some CO2, and then we measure the amount of time it takes until that fish is unresponsive. And that's going to be our dependent variable. And of course, the CO2 concentration will be our independent variable. And so we're going to do this several times with different fish, and each time we're going to vary the concentration of CO2. It's not something that's easy to control. We mix some acetic acid and some baking soda and dump it in the water, but depending upon how much you add and how much water you've got, it can vary. We can't control this very well. So, pretty much each time, every fish is going to be exposed to a slightly different concentration of CO2. Now, we expect that as CO2 concentration goes up, the fish will get knocked out quicker. So that's our experiment. And so we can go back to this little flow chart that we've used. Because the first thing we always want to do is graph the data. We want to see what the data look like. And so unresponsive time and CO2 concentration, those are our variables. And we already mentioned that CO2 concentration is the independent variable. And we think that unresponsive time depends upon the CO2 concentration. And CO2 concentration is continuous. It could take on any number of values. And so could unresponsive time. So they're both continuous. And so according to our little flow chart, we should use a scatter plot. And you've done this before. And so here's an example scatter plot. And again, CO2 could be, an infinite number of possible values, take on any value. And so we'll treat that as a continuous variable. And so then we've got the time to unresponsiveness on the y-axis. And so this is our scatter plot. This is how we're going to graph the data. And is this what we expected? And now, it's possible that I misspoke earlier. I can't remember. But this is sort of what we would expect, okay? That the higher the CO2 concentration, the quicker the fish go unresponsive, the quicker we can knock them out. I don't know if I said that right earlier, but I'm saying it right now. And so you see sort of a downward sloping trend. It kind of looks like it's behaving like we would expect. There's a pattern here. And so it looks like CO2 had an effect on time to unresponsiveness. And again, we are eyeballing the data, and we see that kind of a pattern. And so it looks like a pattern here. And of course, that's what we're trying to do, is look for patterns. And this is a slide we've seen already. Again, we're really just trying to find patterns in the natural world. We believe that there are laws which govern the natural world. And if there are laws, then things should behave in a predictable manner. That's what a pattern is. And so, as a scientist, we believe that many things are not random, but there is a pattern, and we're just trying to figure out those patterns to figure out those laws. Science is about understanding the natural world and how the natural world works. And so if we add more CO2, the fish get knocked out quicker. That's a pattern. And that seems to be the case in our experiment. Now, look, here's a different experiment. And do we see a pattern here? And, I do. I see sort of the opposite pattern. Like the higher the concentration, the longer they go out. So that would be an interesting pattern as well. We want to find those patterns which are going to help us understand what's going on. Do you see a pattern here? Kind of, but you've got this one point down here. Let me get my pen. You've got this point here that is kind of off, so it's not as clear a pattern. Do you see a pattern here? You've got this point here. This looks much less of a pattern, right? It looks like no matter what the CO2 the CO2 concentration has no effect on time to unresponsive. It's kind of all over the place. And so that's the thing. We're just looking for a pattern in the scatter plot. But of course, like we've talked about, that's just eyeballing the data, and that's going to be subjective. And so we need an objective way to try to determine if a pattern exists. And of course, again, here, do we see a pattern? You kind of do. Maybe you see a pattern. In the last one, I don't really see one. But the point is, it's very subjective. And so we want an inferential stat. Does a pattern exist, or are things more or less random with respect to one another? And so that's what our inferential stats will do. And the inferential stat that we're talking about today is linear regression. So again, depending upon the type of variable you have, the type of experiment you're doing, determines what's the best kind of inferential stat to use. And so how do we know which one to use when? That's why you're here. That's why you're in school. That's what you're learning. And so we've talked about a t-test and an ANOVA. Now we've got a new one called linear regression. And this is best when both variables, the dependent and the independent, are continuous. And so that's usually when we do a scatter plot. So if you're doing a scatter plot, you're probably doing something like linear regression. Again, there are lots of different stats out there, lots of different ways to analyze the data. We're keeping it simple here. And so this would be a good way to analyze our data. And so our CO2 anesthesia data that we just looked at, well, that's two continuous variables. So linear regression is appropriate. And so, again, contrast this with the stuff that we've looked at earlier. The independent variable is not discrete. We did not put it in groups. We just took whatever value was, that we could get, or whatever value was given to us. It's hard to control the concentration of CO2. And so, we could put this into like low, medium, and high, but we'd lose information. And so by using linear regression, we keep that continuous variable and we can get more information. And so like before, we had discrete groups. There was not a continuous independent variable. And so linear regression would not be necessarily appropriate. Now, full disclosure, the math behind them is very much the same. And you could definitely analyze this experiment with a linear regression, but it would be essentially the same as doing it in ANOVA. And ANOVA is just easier to run and interpret, quicker. So understand that although we're looking at some of these different ones, like the t-test, ANOVA, linear regression, kind of behind the scenes, the math is very similar. Don't worry about that. Just realize that, ANOVA was appropriate here, but this is going to be something that we're going to use linear regression on. And so what linear regression does is it gives us a trend line or a line of best fit. And so, if I were just sitting here trying to draw a line, kind of connecting these dots, I don't want to connect the dots, I need a straight line. But what's the line that sort of best represents this relationship? That's what linear regression will give us. And so this line of best fit is the line of best fit. It is the line that best fits these data. There are an infinite number of lines that can relate the CO2 concentration to the unresponsive time. So I can draw any line and come up with a way to relate them, but there's only one best line. What makes it best? It minimizes the sum of squares. Remember we talked about the sum of squares when we did variability? And so, you take each value and compare it to the mean and then square that difference and sum them up. And so lower sum of squares means less variability. So although there are an infinite number of lines, there's only one that minimizes the sum of squares. And that's the one that we use for the trend line, and that's what linear regression gives us. And you can see here, it gives us the equation for that line. And so we can directly relate the independent variable and the dependent variable. And so if you gave me a concentration of CO2, I could estimate how long it will take to knock out a bluegill. Because now I have this relationship that relates those two based upon the data that I've collected. And so say I've got 200 parts per million of CO2. Well, I just plug in 200 for X, and then I solve for Y. And so when I solve for Y, it's 443.09. So if I've got 200 parts per million CO2, then I would expect an average bluegill to get knocked out in about 443.09 seconds. That's how we can use this equation and this line of best fit. So it's very powerful because it gives us the actual relationship between the two variables. And so that's what I'm saying here. Now, here's the problem. I've got that line, and I have that equation, and I can do that relationship. I have the best fit, but I don't know if it's a good fit. I don't know if I can trust that best fit. These are the best fitting genes that Kramer has. But are they a good fit? No, they're too tight for him. All right, so that's kind of the idea here, is that you have the best fit, but is it a good fit? And so, again, how do I tell if this best fit is actually a good fit? And I don't want to eyeball it. I use the stats. Well, we've got some stats right there with the equation. Now, the first one we have not seen yet, and it's called the R squared. And so the R squared just tells us how close the points are to this line of best fit. And it goes from 0 to 1. It's like a percentage. It is a percentage. It's the percentage of the dependent variable that's explained by the independent variable. And so the closer it is to 1, the tighter the fit to that line. The points will be closer to that line. And the closer it is to 0, the further away. So it's sort of like the spread of the points around that line of best fit. So if you look on the left, I've got an R squared of 83%. That's a pretty decent fit. That's close to 100. On the right, I've got the same kind of graph, but you can see the points are more spread out. They're not as tight to that line. And you can see the R squared is lower. It's not as good a fit. So that's one way to determine if this line of best fit is a good fit. And if I look here, there's essentially no pattern. There's really no visible relationship between CO2 concentration and unresponsive time here. Yet I still got a line. I can always fit a line to a set of points. Doesn't mean that line is any good. And so that's why we have to evaluate the quality of that line. I can always find a best fit, but it may not be a good fit. And so the R squared is good for that, but you also saw that we had a p-value. And you know what a p-value is, and the p-value is what really tells us if we've got a good statistically significant relationship. And so if I've got a p-value, that implies that I've got hypotheses, and we're using the p-value to test those hypotheses. So my question to you is, what would be a good, null, and alternate for this experiment? I'll wait. Well, remember, the null is the nothing hypothesis, that nothing is going on or there's no relationship. And so our good null would be that CO2 concentration has no effect on time to unresponsiveness in bluegills. So there's nothing happening. Of course, I think there is a relationship. That's why I did the study. And so I need to collect data to convince you that I'm right, which is why I did the study. And so the alternate is the CO2 concentration has an effect on time to unresponsiveness in bluegills. Mutually exclusive. If I can reject the null, then I support the alternate. But we're going to start by assuming the null is true. And so now I look at the p-value. And I see the p is 0.03 for this relationship. And so what does that mean? If our alpha value is the traditional 0.05, what does this mean? Do we reject or fail to reject the null? Since p is less than alpha, we reject the null. So although we assume there's no relationship, based on the data we've collected, we can reject that null and say there is a relationship. And CO2 concentration does have an effect on time to unresponsiveness in bluegills. Now, in fact, we can say a little bit more. We can say it has a significant negative effect. Because if you look, the slope of this line is a negative number. And if you look at the line, it's got a negative slope, which means as the dependent variable goes up, the independent variable goes down. That's a negative relationship. So we always want to be as precise as we can so we can reject the null and say that CO2 concentration has a significant negative influence on time to unresponsiveness in bluegills. Neat. That's linear regression. And that's what I'm saying here, is we not only do we know there's a significant effect of CO2, we know exactly what that effect is. It's a negative effect. And so I can predict the time to unresponsiveness for any value of CO2 in the range that I tested. And so that's it. Since our independent variable is continuous, we need a different inferential stat. The one that we're going to use is called linear regression. It calculates the line of best fit that relates the two variables, but we don't know if that's a good fit. We look at the R-squared and the p-value to decide if it's actually a good fit and a statistically significant fit. And so there's an infinite number of lines that can relate these 2 points. There's only one best line that minimizes the sum of squares, but that could be just the best of a bunch of duds. Just because it's the best fit doesn't mean it's a good fit. And so here again, we've got what doesn't look like a pattern, but we still were able to fit a line to it. But is this line any good? Well, let's look. Our R-squared is very low, and our P is very high. And so in this instance, we'd say this is not a good fit. And so we fail to reject the null. And so we cannot say that CO2 concentration affects the time to unresponsiveness. Based on our data, there is no relationship. We came up with a line, the equation is right there. So no matter what, I can create an equation. Where's mine? Here we go. No matter what, I can create an equation, but that equation is not trustworthy. And so a good question is, what's more important, R-squared or the p-value? And I would argue the p-value, because the p-value is the same p-value we've been using. It tests the null hypothesis. And so we always start by checking the p-value. The R-squared is useful because it's good for comparing different lines of best fit. Earlier, we saw a couple different lines, and one had a better R-squared than the other. That means the points fit it better. There's a lot of things you can learn from the R-squared. Like there might be more than one independent variable that's influencing your dependent variable, things like that. So the R-squared is useful, but the p-value is where you should always start. Usually, when the p-value is high, the R-squared is low, but not necessarily. P-value is the ultimate arbiter. And so, since our data are not random, we reject that null, means we have a pattern. As CO2 goes up, the fish go down quicker. Could we be wrong? Could there actually be no relationship between those two? Of course. We can always make a mistake. However, what are the chances we made a mistake? About 3%. Again, go back to what the definition of the p-value is. The probability we would get these results if the null were true. And so, based on linear regression, there's only a 3% chance we would get these results if the null was true. So we can confidently reject the null. Now, could we make a mistake? Yeah, we can make a mistake. But we can quantify our uncertainty. And that's the important thing about stats. Anyone can make a mistake and can, in a lot of situations, can you say, well, what are the chances you're wrong? Well, I don't know. But with stats, we can have a decent idea of what are the chances that we're wrong based upon the data that we've collected. So there you go. And so that's the idea behind linear regression. Next thing we're going to do is you're going to have some homework where you're going to get practice. We're going to do this in Excel, making scatter plots, doing some linear regression. And so if you've got any questions, let me know. Otherwise, I will talk to you later. Have a good day.